Okay, so we're going to work this homework problem, and we're hopefully not going to do it with that particular line right there. Here's what we've got. Okay, we've got a viscometer. Well, so this will be my key, provided I don't, make any major errors. This should serve. So we've got this system here. It's got this strange sort of, not really that strange, really. The idea of this contraption is that you've got a fluid in this gap right here, right? And depending on how viscous that fluid is, will determine how fast this weight over here falls down, right? Because the weight is attached to this rope, and the rope is attached to the outside of that. I guess you could think of it as a lever, or I mean, they've got it labeled as a pulley. That's not really a bad way to think about it. And so what's happening is as that thing pulls, it's causing this thing to spin like this. And of course, if this were full of honey versus this were full of water or air or whatever, will determine, basically how sticky it is on the outside edge. Okay? So I'm going to show you exactly what I would expect for homework. I don't think anybody did exactly what I expected. I haven't graded it yet exactly, but we'll get there. Okay, so we're gonna walk through this one step at a time, exactly what I would expect, and we'll see. Okay, so I'm gonna assume that you have a copy of that in front of you, so because I'm not gonna write on that. The first thing we would do is that you would be on engineering paper, so you would have a nice line at the top somewhere that you could work with, and you would start by filling that out with usually homework 2 or viscosity and shear or whatever it is you want. Okay, and then there's going to be there's a vertical line somewhere in there. And here you would identify the class that this is for. This is primarily for your benefit, just so you have some organization, so you can kind of find this and know what it is. When you find this sheet of paper a year from now, you're like, what is that? Or, later this semester when you're like, I want to study the old homeworks, right here, this could be your student ID number. That's usually what I want. I think in the thing for the homework, for the key on Moodle, I told y'all to put a name. Name would be fine for this. I don't want your name on your exam, so that's a little bit different. Okay, so then this would be, this is the first page number, and I'll put, the total number of pages there, but, we'll do that when we get there, okay? So, all right, so now we need to know what's given. Okay, now I'm labeling this number 1, although it's the only problem for this assignment. So what's given? A lot of you guys are going to skip this step. You're going to skip the drawing step, and I'm not going to make you watch me draw it, but you need to draw it. It's something that's given. Okay, so here we go. I'm going to draw it. All right, so there's the drawing. For those of you who don't want to draw it, that was like less than 3 minutes of work. Okay, and that's with the straight edge. Okay, now note that this is not a perfect drawing, right? I can't draw those curves for the circles very, perfectly. But the straight edge just makes it all nice. Okay, so we want to use all that. Oh, one thing I did forget. The gap there is A, right? So that's the annular gap, as they call it. Okay, so they give us a little bit more information. They tell us, for example, that we've got a linear velocity profile of the fluid. Okay, that's in the fluid, in the annular gap. So the annular gap is just a gap between 2 cylinders. The cylinders are concentric cylinders. Let's see, we've got a falling mass at a constant velocity. Velocity of V sub m. Okay, and that's it. Let's see, so that's given. And so then let's see what's required. Okay, so what's required is, let's see here, required. The first thing they ask is they want to know what is the viscosity as a function of the mass, gravity. So this is the mass that's attached to that, that's this mass right here. The velocity at which it's falling. The radiuses, or the radii, okay, A, the annular gap, and H, okay, equals what? Okay, the other thing that they want to know is they want to know what is mu if, and they give you a bunch of values. So basically, you know, the first bit of this is really the work, and the second bit of this is, can you plug this into a calculator? We can all, including me, screw up the, you know, calculator bit. You know, so it's good to, it's good to check. It also helps you to, it kind of reminds you like, hey, I need to check my units here, you know. What was this, 50 millimeters? So these values were listed in the problem. A lot of millimeters here, which is annoying, you know, because at the end, you know, we're going to need to convert a lot of these to meters. And you might say, well, I don't want, what if I just, because they're all millimeters, can I just use all of those in millimeters? And there's probably a way you could get away with that, but you'd have to convert gravity to millimeters, and your viscosities would come out in unusual units. So just something to be aware of. I'm going to convert everything to meters because that makes my life a lot easier. Okay, so before I do this, so here's the solution, and maybe I'll start the solution over here because I can see my original drawing here. So for my solution, and I'm not really good at drawing circles, and I don't really expect you to be good at drawing circles, but I'm going to pause this while I draw the circles because, you know, you're not going to want to see this, but I'm going to do a free body diagram from above. Okay, so yeah. Okay, so here's my circles. I figured out a way to get the computer to draw me the circles, obviously. And so I'm looking at this from above, and so the first thing I've got is I've got this weight over here, right? And it's pulling with a force of mass times gravity on that rope. Okay, the other thing that I'm going to have, and this is going to be the more interesting one, in my opinion, and of course this is the point of this question, you know, so this is just the inner cylinder. So this is this, let's see if I can outline it in red. You know, this is this inner cylinder here, right? And so all around the outside of that, if this weight is causing it to spin, in this case clockwise, the thing that's stopping it from just kind of spinning out of control is that there's all these forces on the outside, right, all around it, which is, you know, you could think of it as friction, but it's not really a friction, right? It's the viscosity of the fluid. It's sticking to that wall and it's trying to keep it from spinning, okay? And so we would call that force the shear force, okay, tau shear, times the area. Or let's just call it the shear force. Okay, let's call it the shear force, F shear. Okay, and if this is a free body diagram, you know, the reason this thing is not going anywhere is because there's a pin right here in the middle somewhere, and that pin is, you know, it's got a force going up this way, which let's suppose I call that O. So then this point would be O in the Y direction, and this point would be O in the X direction, right? So you should remember all this from statics. All right, so now what we're going to do here, oh, I guess maybe I should label some, so this right here, that distance is little r, and this distance out here, okay, that distance is capital R, okay? So what we're going to do at this point is what I want to do is I want to say, okay, the reason I drew this free body diagram is because I was thinking about this, and I was like, well, this thing is spinning at a constant rate, so it has no angular acceleration. So just like we might, let's zoom in a little bit. So just like we might at some point say, okay, well, the sum of the forces equals mass times acceleration equals 0, as we might do in statics, and we do that if the acceleration is 0. In this case, we have no, this thing is not accelerating in an angular sense. So I can say the sum of the moments around point 0 equals 0. Okay? Anytime you sum forces, sum moments, you're going to need a free body diagram. That's how I knew I needed a free body diagram. So when I grade this, I'm going to look for a free body diagram. So here we go. So we've got a couple. We've really got only two forces if I go through O, right? So I've just got mg, okay, and then I've got the F shear. So mg has a moment arm. Okay, so mg is causing things to spin clockwise. So it's going to have a negative sign on it. Okay, and it has a moment arm of little r. Okay, F shear, on the other hand, it's got a moment, well, let's just say F shear is causing things is trying to make things spin counterclockwise, so we'll get a plus F shear. Okay, and then its moment arm is that capital R. Okay. Now that F shear is coming from the fluid, okay, so we can expand that. So I'm going to keep this as negative mgr plus that F shear, as it always is from a fluid, is tau times the area times r over which it acts. Okay, so this is the F shear in parentheses right here. That equals 0. Okay, now both of these terms, the tau and the a, both need some kind of like thought process. So you'll see in my work, like a lot of times if I go straight into this and I realize I need something, you'll see that I'll do what I call asides. Okay, so I'm going to do an aside. I'm going to do 2 asides. One aside is going to be to talk about the area that we're looking for. And one aside is going to be to talk about tau. Okay? And so let's zoom in and let's do these. Okay, so for the area, I'm going to do a quick sketch. Okay, and this is a sketch of the cylinder, the inner cylinder. Okay? And what I want to think about is I want to think about the area over which the shear stress is acting, right? And so we have 2, defined length scales on here, or lengths. So we've got this capital H and we've got this capital R. So this area, if I really stare at it, well, it's the area of this kind of like, it's a curvy space, right? So one thing, of course, is when we see a curvy, we know there's going to be a pi in it, right? But it's all this area up here, kind of colored in red, okay? And the hard thing about this is it's like, what is the area of that? Right? No one ever teaches us how to get the area of the outside of a cylinder. But what we need to imagine here is that if I took some scissors and I just snipped it, let's suppose I snipped it right down there and I unrolled this sucker. All right, so I would unroll it and it would look like a rectangle. Well, hold on, I'm going to use a straight edge because, I try not to be too much of a hypocrite. I tell you to use a straight edge. But notice, straight edge doesn't add that much time, right? That line took a split second longer to do it with a straight edge than with that one. It just looks a whole heck of a lot better, right? So if I stretch this thing out, there you go. Okay, straight edge, boom. Okay, now this dimension is still h, okay? And then this top dimension right here, okay, if I look at that, well, that's this thing right here. That's the, quote unquote, the length of this circle, or what we call the circumference. So this is going to be 2 pi r. Okay, so the area is length times width, so it's h times 2 pi r. Okay, so the area equals 2 pi r h, 2 pi r h. Okay, now we're going to go down to this tau, right? Because that's the next thing that we need to deal with. Okay, so I'm going to draw a circle. Okay, so we've got this circle, and one of these days I'll learn how to draw one that's not all filled in like that, but whatever. All right, and it's spinning, right? And as it spins, there's 2 circles, aren't there? Hold on. Okay, and these aren't perfectly centered, but anyway, there's 2 circles, right? There's an inner circle and an outer circle. And we don't really care what's going on in this inner circle here, right? This inner circle, I don't even think, oh yeah, we know that the inner circle has a radius of capital R. And we know that the gap in here between these 2 cylinders that's filled with fluid has a length scale of A. Okay? So I could, give you some points here. And so what we're going to do now, as I clean up those lines, but what we want to do is we want to think about what the fluid is doing. For some reason, I went off on an angle here. But we want to think about what the fluid is doing in between those, okay? And this outer circle is not moving, but the inner circle is moving. So the inner circle is spinning like this with the, angular velocity of omega. Actually, that's the wrong way, isn't it? Yes, that's the wrong way. Anyway, so it is spinning with the angular velocity of omega. Okay, and as it does so, the fluid around the outside of it is being pulled along, right? So the fluid on the inside, I'm just going to do one velocity profile. I'm not going to draw it all the way around because that just seems excessive. So here's a velocity profile. So out here, the fluid is not moving. And on the inside, the fluid is moving at whatever the speed the inner cylinder is moving. Okay, it's moving at a complete right angle. Okay, obviously this creates a few issues that that we'll have to deal with at some point, but anyway, not today. And so we get a velocity profile that looks like this, right? So for lack of a better term, I'm just going to call this VC for the velocity of the cylinder. And out here it has a velocity of, right here it has V equals 0. Okay, so usually that's V sub theta, okay, because it's the velocity in the theta direction. But then the distance between these two things is A for that angular gap. Okay, so why are we doing all this? Well, we're doing all this because tau equals mu du, in this case du theta, divided by dr. Okay, so I'm going to zoom in. So tau equals mu. Now the du, that's the difference in the u theta, or the velocity in the theta direction. So we'll solve for that by going from, one velocity to another. I'm going to go ahead and do an absolute value here just because it just kind of, I'll keep track of the sign on my own. And we'll start out here and I'll say, okay, well, we've got, a velocity of 0 on the outside minus a velocity of VC on the inside. Okay, and I'll compare that to the radius here versus the radius on the inside, which is a total distance of A. Okay, so ultimately we're going to get tau equals mu VC over A. Okay, where A is just that angular gap. Okay, so it's going to have units in millimeters or meters or whatever that might be. Okay, so we're going to plug that in over here on the left, and we're going to plug this in over here on our left. Okay, so we'll go back over here to our original equation. Okay, let's see here. So we're going to say, well, negative mgr plus tau times A. Well, tau at this point is something, we're going to plug in for that. So that's going to be mu BC over A. And then times the area. Well, what's the area here? It's going to be, let's see, 2 pi RH, 2 pi RH, like that. Okay, and I've still got this R equals 0. Okay, so the last thing, like this looks pretty good. Like it looks like I could probably rearrange this for mu. And in fact, let's go ahead and do that just so we can see what else we need to do to see if we're done. So the first thing I'm going to do is I'll bring this over to the other side. And then I'll multiply that A times both sides, and I'll do some division. And I think we're going to end up with, okay, something like this. Okay, so let's see, mu equals, we've got the M, we've got the G, we've got the R, we've got the A. And then on top, we've got the, let's see here, the 2 pi, the VC, the R squared, and the H. Okay, yeah, so we got all that. Okay, so that's what we get. And we might be inclined to stop here. Okay, the problem that we have, and so this is going to require one more thought, is that if I go up here to the initial question, where is it? Right over here. Okay, we need this in terms of Vm, right? So that's the rate that the mass is falling, and we don't have that, right? So if I go back to this original drawing, okay, we look at where it's where it's kind of coming in. It's coming in at a distance of r, right? And so we have to think about that, but we've got this thing solved in terms of something that's out here. Okay, so I'm going to draw another picture, and we're doing one more aside. Okay, and this is about velocities. Okay, so we're going to do an aside on velocities. Okay, and I'm actually going to use these circles up here because this actually makes perfect sense. Okay, so I've got, for this aside for velocities, I've got a velocity right here, which is VC, right? Oh, no, sorry, that's the fluid. No, the fluid and the cylinder, right? So they're, that's right. So the fluid and the cylinder are moving at VC at that distance out. However, let me, erase a little bit of this, and let's talk. Right? I don't know why it won't let me erase at the moment, but I wish it were. Okay. So, what's going on with this cylinder, and really all cylinders, or all spinning circles, really is that as you get further out from the center of the cylinder, it's spinning faster and faster, right? Because it's all moving at the same angular velocity. But the further out you go, it's the same number of rotations per minute, but a rotation means more the farther away you get from the center. So we've actually got another circle in here, and let me see if I can draw that circle. There you go, and you can almost kind of make out what the velocity is right there. It's like right here, right? So it's not quite so big, right? And that velocity right there, that's v sub m, right? That's the rate at which the weight is falling. Okay, and that's actually what's causing all of this to move, right? So you might say, okay, well, whatever. How do I get from one to the other? Well, we could do some sort of linear interpolation, and essentially that's what we're going to do. But I'm going to think about it a different way. The way that I'm going to think about it is this whole thing has one angular velocity, right? So usually you define that as an omega. Okay, so the omega as defined at this distance, okay, which is a little r, is the same as the omega as defined at this distance, which is a capital R. Okay, so maybe I could just call that omega at r equals the omega at capital R, okay, because they have the same thing. Well, omega, if you remember your linear velocity, can be defined as v at r, which I think, what did we call this v at r? Oh, we called it v sub c, right? So v at c, oh wait, sorry, we're at little r, sorry. All right, so we're going to be at little r. So let's analyze this at little r. So at little r, this is the velocity. You'll remember that it's v sub m. Okay, so what we do is we take the tangential velocity and we divide it by its radius. That's how you get the angular velocity. Okay, so v sub m is acting at r, and that is equal to, at capital R, right, this is the velocity, and we divide it by its radius, like that. Okay, so based on my equation from earlier, what I want to do is I want to solve for VC, so I can get rid of it in the equation over to the left. Okay, so VC then is going to be, let's see, Vm times, looks like it's going to be capital R over little r. Okay, and we'll box that, and we're going to plug it into my big equation over here. Okay, although it's really not that big, right? Okay, so in other words, we can't stop here. Let me zoom out a little bit so I can actually see my dots, because that's what keeps me neat. Okay, I'm experimenting with the dots. I usually prefer lines, but I guess we'll see what happens here. So I'm going to have 2 pi, and in place of v sub c, okay, I'm going to put the velocity of that mass times capital R over r. Okay, and then we've got what? Pi r squared h. Oh no, wait, we've got r squared h. No pi. Pies are delicious, but they don't belong everywhere. Okay, so we'll say mu equals, and then if I rearrange that, I get m. Let's see, how did I rearrange this? Let's see, mga r squared. For some reason, I wanted that r squared out front when I did this, but we're gonna say 2 pi v sub m r cubed h. Okay. So there's your solution to, I don't think it called it part A, but whatever. All right, so then looks like I've run out of room on the first page. So we're now kind of working on a second page. So let's go ahead and let's do a second page. I'm only, putting a second page in here so that I can show you how to, how to do your page if you're concerned. So it would look like this. It would look exactly the same as the last page. I'll go ahead and do this on the down low. Okay, with the only difference being that now we are on page 2. And in fact, I know that this is only going to take 2 pages. So I'll go ahead and put a 2 there, and I'll go up here, and I'll put a 2 here. So this is the first page of 2. This is the second page of 2. Okay, so to finish solving this problem, we will, I need to find where I finished this, oh, right here. And so basically, I'm just going to plug these numbers in. So I'm going to say mu equals mgr. Oh, man. All right, I'm a little out of order here. mgar squared over, 2 pi vm r cubed h. Okay, so we're just going to plug these numbers in. Okay, and all of these numbers were given. Okay, 9.81 meters per second squared. The A is 0.20 millimeters, so we'll go times 10 to the negative third meters. Okay, and then this was 25 millimeters for R, so we'll go 0.025 meters squared. And then underneath that, I'm going to get 2 pi 0.030 meters per second. It's not falling very fast. 0.050 meters. This is going to be cubed. And then 0.080 meters. Okay? So those are just numbers from the problem. So if I plug all that into my calculator, and on a problem like this, I recommend plugging it in several times, which is what I had to do to make sure that I got it right. I can't believe it, actually. I got it right the first time, unless I got it wrong every time, which is certainly possible, right? So we do that, and then if I'm going to look at the units, right? So I got kilograms times meters per second squared. Okay, those first two things. That's going to be a Newton. And then it looks like I've got meters cubed up here. Okay, and then what do I have on the bottom? Well, I've got looks like I've got meters to the fifth per second. Okay. So if I kind of arrange all of that, and of course I'm going to round this to 3 sig figs because that's how we do it in this class. I always want 3 sig figs. And my final answer is 0.0651. And let's see here. So that's a Newton. This is a Newton. And then I've got times seconds, because the seconds come to the top, over meters squared. Or really probably the easiest, and maybe not the easiest necessarily, but the nicest way to put this would be a Pascal times second, a Pascal second. 0.0651 Pascal seconds. Or you'll sometimes see this converted into centipoise. The only nice thing about a centipoise is it's not so small, right? Centipoise. I never use centipoise. I highly recommend you do not. One of the questions here, is like, well, is this a reasonable number? And when you're doing this for homework, I highly recommend just check to see if you got a reasonable number. So, I typed into, Google, the internets, what a typical absolute viscosity is for a lot of different fluids. And it really seems like the highest one they've got in here is glycerin, which is 950 centipoise. So 950 centipoise is for glycerin. And the lowest ones that I can see here are less than 1. Let's see, what is the lowest? Maybe carbon disulfide, whatever that is. There's a refrigerant called trichlorofluoromethane refrigerant, R11. That's very low. Or here we go, propane. Propylene looks like the lowest. Anyway, the lowest, so this is the highest. And the lowest that I'm seeing is about 0.09 centipoise. Okay, so this is kind of the range. So we're comfortably on the high side. Okay. Obviously, you can imagine a case where, I don't know, if the fluid were moving a lot faster. So if this number right here were a lot larger, okay, then it would be moving faster because it would have a less viscous fluid holding it back, right? So if it moved faster, so if this number were bigger, then this number would be much smaller, okay? So that's another way that you can kind of start thinking about, your final equation and things like that. But anyway, I hope this was helpful, and that's all I got. So focus on the fluids aspect of all of this, not so much on the angular spinning. I wanted to give you kind of an interesting problem, and I found this one interesting. So I hope you're having a good one, and I'll talk to you later. Goodbye.